some deep insights. I tried to explain some yeah, I understand it was quite technical, but you cannot explain what is LLM, what is agent without going at least that deep into the technical details. Some deep insights that help us to understand what are the bottlenecks, how to improve, what to pay attention at, and the root causes of these problems. First of all, we need to understand what is the agent state. Again, as I said, every time we call LLM is just a tool that produces a new text. It doesn't store anything. Whatever you put as the context, it will use to produce a new text. If you want to restart your conversation, not restart, but continue your conversation with the next call to the LLM, you need to put this previous text explicitly. Nowadays, all the chatbots do it by themselves. All agents do them by themselves. However, we need to understand what goes inside, because the longer we have a conversation, the more trash, the more history, the more context the more tokens we put again and again. And in this case, yeah, I already talked for an hour. Do you remember all my words? You don't need. But if I were the agent, every time I ask the LLM, I would put all the conversation again and again and again. So it's exponentially growing context. And in this case, it is very critical for memory leakage, for token utilization, for everything to understand what is the agent state. So basically, agent state is everything that agent needs to persist between two steps. So after the agent receives the answer from the LLM, it decides whether it should go to the next round or give the answer to the user. If it decides to go to the next round, it should preserve all some necessary information in order to, at the next round, create the proper instruction, proper context from this information. What does the agent typically store? Working memory. So it's a current task. If it's a maybe user query, or if it's a sub-agent, the task from the previous agent. Recent observations, intermediate results. So something that some notes based on the previous steps, maybe reasoning, maybe thoughts, whatever. Now the goal, basically what we are trying to achieve. Typically, when we try to solve something by ourselves, we definitely think about what should we achieve rather than the steps that we need to do in order to achieve something. Context or history, again, this is something that gives more clue to the next call of the LLM to make it more accurate. World model. One of the most forgotten parts. When we explain the world around the model, let's say, typically we say, you're agent or you're a good assistant, you work for the Llama software company. So you give some environment information which may give a lot of sense to the agent, to the LLM, because LLM needs LLM is like a writer. If you start from the middle of the sentence, from the middle of the book, you would never understand what's going on in this book. So you need to give more and more context, and in this case, the LLM would act accordingly. And tools, resource state, I can explain what are the tools, what are the open files, maybe some active sessions of tools that I don't need to call. So some technical stuff. This is the agent state. of each agent. So after the agent finishes its job, its call, if you do not close the session, the agent would store these in the memory. It definitely speeds up the next question. It doesn't need to run it more and more and more. It's a state. Every time you ask a new question, the state is updated. When the agent passes some information from one agent to another agent, it may pass its state as well. However, the decision of what should we pass from one agent to another agent, again, depends on the use case, depends on the agent, depends on what you want to achieve. And basically, let's say, what we always pass from one agent to another agent? Ask an instruction. So when one agent asks another agent to do something, it's obviously it should keep the task. Some context, so some relevant slice of prior results, maybe prior thoughts, maybe not the full history, because the full history is maybe redundant for the purposes. Sometimes past some state of this agent, if this state is relevant. Again, not the full dump. Prior results of maybe this agent was already been called by this agent. So and this agent decides that this agent was wrong. I give the prior result. Maybe explain how to access the tools. Some constraints, so some guardrails saying don't do this or whatever. And rarely past some full history. In rare cases, I can just give a piece of valid history, not the full one. Scratch parts. So again, you name it. We need to understand that if we pass all the information, this agent may not even require 99% of all that information, and this will just increase the cost spending. It will increase the latency. Whatever. Now, agentic network bottlenecks. Let's look at few basic architecture and understand. Like here, I said there are multiple of them, and we need to understand, like, decide what to use before we start the project. When we decide to use the agents and so on and so forth. And now let's think about how should we do this. In order to do this, we need to know the pros and cons of each of them, and know the bottlenecks that we can face using each of them. Let's say, let's look at the sequential agentic network architecture. So we have the agent A that calls the agent B, agent C, and so on and so forth. The agent A does its job. It has some context window, and so the result and some prior history fits this part. When I pass this information with the prior history to this agent, it adds some more information to this window. And next adds more and more and more. So the longer the chain is, the more information is passed through these agents. And at some point, the prior historical information may hit the full context window, and there will not be a free space for the reasoning, for the thoughts. It will just stuck. Another one, let's say if this agent creates an error, the calculator gives not the proper number. This agent would use this number. So the error enters, and it starts progressing, and all the next thoughts potential, like in most cases, they would be incorrect. Now, let's say if this agent fails, this agent would never be achieved. So again, since we have the direct, straightforward architecture sequential, if the chain breaks everything. So no parallelism, single point of failure, error accumulation, context rot. So again, more context we have, less space we have to for a real job. Token overuse. Every time I send a new request, sending the same history. So I process the history here. Now I process the history as well here. I process the history as well here. So I 3 times or even 4 times I use the same history. I don't need this. Hierarchical architecture. In contrast, let's say we have an orchestrator. We have a single place of simulation of the results. And let's say this agent gives the result. It may give some not the best one. So and the error may be spread to other ones. And let's say one of big risks here is, let's say this agent may give some bad result. The orchestrator may understand that this result is bad. It may say, no, you're wrong. Let's do this again. And you can go to recursion. And they may argue, no, I'm good, I'm bad, I'm good, you're bad, and so on. And it may just eat your old tokens, make it stuck, like ruin the universe, whatever you want, whatever you expect. So the performance is quite slow because the orchestrator, every time the agent finishes its job, it goes back to the orchestrator, and again, orchestrator needs to think. So the performance is quite, like the latency is quite high. Recursion risk, error misrouting. So the error may be spread across all the agents. Serial bottlenecks. So every it waits, orchestrator waits until this ends. Now it goes here, so no parallel routing. And again, token overuse. The orchestrator needs every time think about the answer and think which leads to next. But the cons of the pros of this are quite good as well. So we have the orchestrator, let's call it LLM as a judge, and this LLM or agent would understand if it's a good or not. So instead of you, it would direct, it would manage these guys to to make them to do their job. Multi-LLM Agentic Network. This is another way of, let's say, how to let's go back. Picking correct architecture may reduce costs, may reduce a lot, may increase the accuracy, may reduce the latency, whatever you say. So again, picking all the pros and cons and carefully understanding what are the bottlenecks are very critical. Another one is the architecture, sorry, the LLM choice decision. It's also very, 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 very critical. Let's say we have a system of several agents, a calculator and analyzer. And as the beginning, we use the same large language model, so very large reasoning model, very large, GPT 5.4, large for like eating the tokens like a horse. And now the calculator just doesn't need the reasoning. It definitely doesn't need. It just needs to convert the query into the tool call and just 2 plus 2. Just convert this into this. We don't need reasoning. However, if we use both large reasoning models, it would take a lot of tokens. It has a higher latency because each of models will just think, and the fast quota utilization, you just fall over the quota. Instead, let's look at all these agents. Analyzer definitely needs to think. it definitely needs to go deep into its analysis. So the choice of large reasoning model is good, is valid. The calculator, it doesn't need this big one. It needs a very small model that just converts the user query into this into two numbers and the sign in between them. That's it. So if I use different models for different agents, I may reduce the token usage, reduce the latency, and potentially, theoretically, get the same result as I had here. And the quoted utilization might even be less. I prefer GitHub Copilot for my daily routine, and I typically switch from like pro models like Claude, whatever, to default models, because default models, they do not they don't have quota. I can use them as many as I wish, every day, every hour, whatever. So I prefer for this very small tasks, I switch to that type of model, and it does the small tasks very good. If I need some reason, I definitely pay some price for that. But this switching to the small model reduces everything without giving the same result. However, exclamation marks. There is a very common bias, very known bias, homogeneity bias, modal homogeneity bias. It says, let's say we have two agents, and one agent gives a request to another agent and gets the response. And both agents, they utilize the same model or even the same architecture of the model. Let's say it's a GPT. GPT-4, GPT-4o mini, whatever. And typically, if the architecture of models, if the vendor of models is the same, the agent may act similarly. So the response would be a proper response. But if I use different vendors, it might happen that one agent, one LLM, may disagree with another LLM with the same response. With the same question response. Why it happens? They are trained based on different data. They are trained based on a bit different architecture. They are trained based on pretty different. And it's the same as imagine that we have two students from the same teacher and two students from different teachers. And typically we may disagree. Tell it to the ancient Greeks. They fought each other. They killed each other because of the philosophical questions. So this is it. So we need to be careful that picking up the correct model is a good way to reduce the costs and to improve your accuracy, improve everything. However, we need to be sure that there is no bias behind them. Let's say DeepSeek. If you remember, DeepSeek, if you ask a question about some genocide, Chinese genocide, it would say, I don't know anything. And the GPT might say, no, you know. And recursion comes. Okay. The thinking and the reflection. Basically, this is the same. So imagine that we have an agent. So coming back again, the LLM produces the next word, the next token. This is the basis. And when I produce, when I create a word by word, I just cannot change anything before. And potentially I may come with not the best solution. That's why typically thinking or reflection is the way how can the agent improve its own response before the response appears to the user. So typically nowadays all the agents, they think it's their common situation. However, I just want to say, like, sometimes we don't need this thinking. The thinking just does multiple times. We call the LLM and try to improve the previous result. That's it. And if the result is improved a lot, like finally, the answer goes to the user. There are some pros and cons. Cons are obvious. I need to run multiple times the question, so the latency, tokens utilization. It can overthink. It can just go to recursion and think, argue with itself. It's a crazy. Sometimes I myself argue with myself, and I cannot stop doing this. The reason may drift. So more every time it goes back, it pushes all its previous thoughts. And imagine that after 10 times it asks itself the same question, the context may become critically big, and it may even lose the context. It may lose the focus and think about something else, completely else. I faced this a lot. But when we think, when we don't think, we may lose the accuracy. So once we thought, that's it. So again, thinking about whether we need to use thinking and reflection or not. Again, this is a decision based on the exact task that you want to solve. Let's say no thinking. It's a simple high volume, low stake tasks. Let's say convert, call the tool. Yeah. If we want, but again, the thinking we can use for the multi-step planning or tool orchestration. If we don't want to, if we need to run multiple tools, yes, or if we want to create a plan, and we need to definitely think before it. If we have a very latency sensitive user experience or UI, so autocomplete in your chatbot, or sorry, in the sorry, whatever, in the GitHub Copilot, you have a auto completion. How do they call it? Grammarly, it's auto completion. You don't need to think, because user would already be at the next paragraph before you finish thinking. So it's chat, whatever. High stakes actions. If you need something very precise, you need to think about before you run the code, or you pay something. Well-defined narrow domain. If you already have something well-defined, if you need to act upon very strictly upon some steps, you don't need to think. Someone had already thought about before you. Or open-ended reasoning research. Reasoning research, believe me, you need to think before you research, and then think during the research. Again, not using thinking decreases costs, decreases latency. Using thinking, in contrast, increases that. Multi-agent debate. This was proposed by, or console. There are multiple ideas behind it. Andrei Karpathy, this is one of the big names in AI. I would strongly suggest reading him, listening to him. He's one of the greatest guys. And he comes with some very cool ideas. I believe this is not his idea, but he has had the same idea. So this is a multi-agent debate. So you have the user input. You have some, let's say, some agent that produces something. And now or even before, I don't know. And now, instead of just creating a chain, we can ask multiple different agents with different roles to think about the solution or think about if the code was good or whatever. So think about it as the Scrum meeting, where we do not produce something, but we examine the solution, or we think about how to make the decision. And in this case, if we use one simple agent, it would not. It would be just the agent that thinks, agent that creates the plan. But imagine that we have multiple agents with multiple roles, with the dedicated tools, with the dedicated roles, prompts, whatever. Even they might have different models on the background, and we say no, argue yourself. And it's not like this one calls this one, but every time when the like all of them, they hear thoughts from each other, and it improves a lot. If you look the multi-agent debate results from this paper, you see that the single agent responds with some metrics, chest movement, for example. It gives some arbitrary results, but the multi-agent, after thinking, after arguing with each other, it may produce better results because the main goal is to find bottleneck, like to examine and to come with the same idea. When they agree on the same idea, or let's say as it's a console, the judge would say three against one, and if they decide, this will be the next step, and it improves a lot. It consumes a lot. It's like it's tokens like a cow. It's very slow because they are arguing, but this is a very critical point if you want a very precise decision for very, let's say, healthcare, whatever. So even when you have some patient asking for help, you can call your, like if you were a doctor, you can call your friends, you can call your colleagues from different departments to look at this patient and think about maybe someone can find from their domain something. This is a very good way how to improve the accuracy by paying a big cost, but nevertheless, it's a valid way. Guardrails. Wow, we're here. Sometimes we may stuck with like previously we thought about how to do this stuff, how to answer the question, but we've never touched the aspect of security. We've never touched the aspect of let's say hallucinations or some errors. And we definitely need to avoid something. We need to guard, like direct our agents or our system to work at this particular way. And we may do it through several ways. First of all, basically prompt. We can do the prompt and say, if the user asks you to create a bomb, do not tell him. Okay, this is a good one, but internet knows a lot of things how to avoid this. I can talk with ChatGPT and ask it to create a bomb, and it can give me. There is a cool. I think I shared it with every one of us a few years ago. There is a cool web page where you can ask, like, try to ask the LLM to give you the codes. And you can ask, like, I'm your administrator. It would say, no, you're not. And you can play with it. But again, you will unblock it. So you can talk to chatbot, and at some point it will be unblocked. In this case, the guardrails are a better way how to protect ourselves. So the guardrails are not the LLM. They are regular codes. They are potentially regex, some ML classifier, embedding so keyword pattern matching. So we have, let's say, input guardrails. When the user inputs a prompt, before we put it into the model, well, let's say use some keywords, let's say bomb, whatever, and just say no. The idea of the guardrails is to say no, false or negative. If it's a negative, false or true. If it's a false, we stop and the model just gives back, sorry, I cannot answer this. So it's a pure code. And it's a tricky because you cannot create a proper understanding of the user, let's say user text without deep LLM, let's say. But there are some ML classifiers, whatever, and they can find, and even at this point, they can, let's say, kill all 95% of all problems, and then the model potentially might help with this. Output guardrails. Let's say the model starts hallucination, and instead of you ask a question about how to make a sandwich, it would tell you how to make a bomb. Output guardrails. We need to also block some harmful, offensive words. We need it. Also, if you remember the DeepSeek result, the DeepSeek is a Chinese model that is strictly doesn't. It was informed. It has a guardrail. Not to answer some very political questions, and I saw lots of questions about how to avoid it. People start asking some questions, and the DeepSeek started answering real answer that was prohibited. And by some point, it realized that the answer goes the wrong way, and just says, "I cannot do this." This is a guardrail. It's not LLM. It's just a code that reads what LLM gives and stops the LLM at the point when the LLM fails. So again, this is guardrail. It's not a technique. It's an art. No one will tell you how to create your own guardrail for your own project. It's up to you. You need to think. You need to again, what the potential bottleneck, what the potential issues, and so on. You can find some code that you can use as a guardrail, but it's art of protecting your system from the user or the user from your system. Good stuff here is the LLM as a judge. Is typically I hear it from many places, but again, we need to talk about it. LLM as a judge is a method. How can we judge if the answer is correct, or if the answer doesn't have any bad words, whatever. We create a separate system, separate agent, not connected to any thoughts. And maybe even a separate model, not that the type of the model, whatever. So it's a very, very separate. And ask this LLM as a simple question: does this input contain something very restricted, whatever? So again, LLM is a judge, and the core feature here, it should say yes or no, not in the middle. It should not think, because if it starts thinking, it may overthink. It may fail into the same problem of a clever user. It should say yes, it seems like, or no, it's a pretty valid. Okay, there are lots of possible guardrail approaches again, but it's an art. Business aspects. I'm sorry, it was quite a long journey, and I'm sorry for the next slide. It's a mess. It was like 2 a.m. at night, but I tried to fit into the next slide as much information from my prior experience as I could. And then when I woke up in the morning, I realized that this is a mess, and potentially it may disappoint you. I don't like this slide. Agent design decision framework. So I tried. There are multiple decisions that we can make based on some. Isn't the project? So basically, whether we need to use the agents or do it manually, whether we need to fully automate it or use a chain of scripts, or multiple purpose agent or single purpose agent. And I try to remember at least 16 what I could fit here, 16 typical questions that could be in the project. Let's say, again, it's by all means, this is not the last judge. You need to apply it for your own purposes. It's just my suggestions. First, like, pay attention. Is the process, business process, well defined and repeatable? If it is, it's a good candidate for agentic approach. If it is not, you should probably stabilize the process first and then apply the agent. Because if the project is not stabilized, your agent may fail. Can the outcome be measured objectively? If yes, you need to define your own metrics. If not, create a successful criteria. So again, this is something very critical. You can create the metric, a number or set of numbers that you can measure the outcome, and then track it. If your agent fails or not, if there is no such kind of metric, you need to have a such successful criteria. So let's say we at least got some. But this is a very, very general for all the projects. And it is very applicable to the agentic project as well. Does the task require multiple steps with the conditional logic? Yes, no. Agent, or just a chain of scripts. And so on and so forth. I can go next, or we can just leave it as it is, and you can just read it. Go on, here as it is. So again, this is by all means, this is not the full list. This is just a vision. How should you decide? Typically people say, I want the AI, I want the agent. And then they say, I want the agent to calculate 2 plus 2. And you say, you don't need this agent. And typically, again, it depends on the project, depends on the client. Typically, when you say to client, you don't need this, you can spend 100 times less money based for this, and this, doing only this. And even I have, in my experience, when we hired some previous companies to make the AI, and I just read the processes, and I figured out the bottlenecks and said, just fix it. And they had the profit. And then they didn't need the AI at that moment. And it was profit for them. That's, yes, not a benefit for me because they didn't spend as much money as we expected, but nevertheless, again, this is something that we need to understand as well as the company. Risk register. Again, by all means, this is not the full picture, but this may help you to understand what are the risks of the system. Not even yes, risks and some problems. Let's say two-dimensional space. Likelihood and impact. Likelihood means how likely this issue may arise, and another one is the impact. Apologies. Is the impact is a high or low impact? Let's start with the low. Background noise. Model deprecation. Maybe Sam Altman may say, I don't like this model anymore. You don't have the access to this model. It's a low likelihood and it's a low impact. You just switch to another model. That's it. Or rate limits. They decrease the rate limits. Whatever. It's a fine-tunable. It's low frequent. High likelihood and low impact. Annoying but manageable. It's a run tools calls, so your agent just may call another tool, or your result degrades the quality of the grades and causes some real damage. But again, it's annoying. It's a debugging. It's just a process of. You just need to monitor the result, some metrics, and just fix it. It's as any system. High likelihood and high impact. This is your biggest problem. This is a problem that you will face 99% of your time, and this is all the problems typical that you need to focus on. Hallucinations or looping agents that lead to cost runaway. So hallucinations, you know what is it? Looping agents, one agent calls another agent, and so on. So and they just drain the token bottle very quickly. It happens constantly, even in production. You don't need to. You must not deploy anything without mitigations. So you need to understand why it's happened. You need to fix it, run it in the dev environment, test it. You know this. But again, this is the biggest problems. And catastrophic ones. The low likelihood with the highest impact. They are rare. You do not expect them. It's a prompt injection. Maybe someone from outside injects some prompt, or some very specific prompt that was like it was not like explicitly intended, but some problem with prompt, and at some point it ruins everything. User data leakage. Like Claude leaked their codes. Yeah, it was a good one. It was based on the agentic problem. Agent deleted the wrong record or all the records. You know, this is a disaster. And you need to design guardrails around this. So the guardrails may help you to basically protect or at least decrease the probability of likelihood of these events. Again, what to do? Design guardrails, input guardrails, process guardrails. You can even put the guardrail after each agent. As many guardrails, more guardrails, and the output guardrail. And this is based on my experience. By all means, it's not the most common one. First of all, development costs and production costs. Let's say we have a cost budget. While developing, we have very low LLM calls and inference costs, because typically, how many? 5 developers at maximum. They develop the prompts, and they do not force this. So we do not spend it on LLMs at all. Infrastructure. You know to set up this infrastructure, set up the MCP. So again, you know it. If you delete all the information about the LLM, whatever, it's a typical project infrastructure. Again, if you raise your system, if your system is scalable, again, you need to scale the infrastructure. And the hidden costs, the biggest for the development, it's debugging, fine tuning, human review, production costs. When we go to production, the majority of spending is LLM because people will train it. But the hidden costs are quite small, so it's basically human review, some debugging, whatever. Approach choice effect. So let's say again, I've already mentioned it. We have a naive build. All large models, all the sequential, full history, context passing, latencies will be very high, and the costs, let's say it's a baseline. But if we mix the small model and a large model, we parallel the where it is possible. We filter the history, summarize it. The latency would be medium, and the cost to run might be even half time less, even more. It depends on the optimized build from scratch. So the main idea is the architecture decision is the budget decision. When you have the architecture, it means that you can already potentially calculate what would be the cost. Model selection is the biggest single level in this decision. Everything else is the everything else. Context length is the silent budget killer. The more context you put, basically why typically the Claude code consumes a lot of tokens, because it passes the context a lot, thinks a lot. It's a context, and it drains the token bucket. Failure rate matters. Failure rate means hallucinations means they're less effective, and it increases cost because we need to ask a human to check it and so on. So again, think about decreasing the failure. Even like if you think that let me do the MVP with low high errors, whatever, it will cost you more than you expect. Do not optimize the costs at the end. You need to design it from the start. How would you optimize it? Because when you have your agentic flow fine-tuned and you want to start optimizing it, you would definitely lose this agentic flow, and you need to change the architecture. Start it from the beginning. Legal aspects. Recently, I read the article about the Vatican made their own legal article about the AI. I wanted to put it, but I forgot. You can just use the link here. It's GDPR and some maybe American. Yes, they don't have the one single paper or acts, but they have multiple across different states. But again, this is something that can be